Hey guys, welcome back. We're continuing day 21, and we're going to talk about bonding real quick. We're talking about multiple bonds versus single bonds, and then we're going to do some more examples. All right, and so the bond energy is the energy required to either break the bond, or you can measure it as the energy released when the bond is formed. So when we make a bond, right, when a bond is made, right, energy is released, okay? Breaking the bond always requires energy. No matter if the bond kind of wants to be broken, it still requires energy to do so, all right? So now the least energy is a single bond, and the most energy is the triple bond, all right? There are quadruple bonds in metals, but we're not going to discuss that right now. We're just going to talk about single, double, triple bond for the main group elements, especially the nonmetals. So if you look at carbon here, which carbon has single bond, double bond, triple bond. If you look, it does go down, right? Now, you're talking not a huge amount, but a measurable difference in picometers. Same thing with carbon single bonded oxygen to carbon double bonded oxygen. I mean, that's 22 picometers, all right? Now, the other thing is, the more bonds, and this kind of makes sense, right? They're stronger. So not only the bond length, as we get more connections, it shortens, right? The atoms get closer together, but that also becomes stronger. And that kind of makes sense, doesn't it? Right? Right? And if you look, it's a significant increase. A significant increase, all right? And so as we increase the number of bonds, the strength goes up. And that's just good information. All right? When we talk about this, because later on, like one of the things we try to do, as we'll get to later on, is take bond energies and harness those bond energies to do work for us, right? Like it's nice to have a lawnmower where you put gasoline in it and you pull it, start it, however you start it, and has an engine, turns a blade, and cuts the grass for you. You don't have to use like an old blade yourself and manually go around swinging it. That's much nicer, right? So we like to do that. And so this is good stuff. All right, we're going to continue on then. We'll transition back to more examples of bonding, drawing Lewis structures, right? Because we've got lots of practice with this. This is very important. Now, the first two we have are ions. They're both cations. So what happens to the valence electron count, right? Because if you remember, we're going to have to count the valence electrons. H has how many valence electrons? 1. And there are 3 H's, and oxygen has 6 electrons, right? Because it's in group 16. But because of this positive right here, we're going to subtract 1 electron, because overall, we lost a valence electron. We didn't lose a core electron. We lost a valence electron. So that would be 3 plus 6 is 9 minus 1. So that gives us only 8 electrons to play with. Right? And because this is an ion, we're going to put, well, who's in the middle? It's not hydrogen. So it has to be oxygen. I'll put 3 H's around. And then we put brackets around to know that this is a positive ion. Because of that, right, the whole thing is charged. Then we can bond 2, 4, 6, and then lone pair, extra goes on the central atom, 8. So now we have 8 electrons around oxygen, and we have a duet for each hydrogen, okay? And so that's good. It's an ion, so it's got the plus. The whole thing's charged. Same thing now with ammonia. And by all means, if you guys pause me and try to do this without listening and then check, it's a great tool. So with ammonia, 5 electrons. Hydrogen, 4 times 1 electron, plus 1, which is negative 1 valence electron because it's a positive charge. So that gives us 5 and 4 is 9, minus 1 is 8 electrons. Middle, central atom, not hydrogen, so it better be nitrogen. You got 4 H's. North, south, east, west is fine, especially at this point. And it's positive. 2, 4, 6, 8. That's good. All I have is duets for hydrogen and 8 for nitrogen. That's all we have. All right. The next one, formaldehyde here. All right, because we have 4 more to do, and then we'll be done with this day. Now we're getting more complicated. All right, more complicated. Okay, so 1 electron, but there's 2 of them. Plus carbon has 4 valence electrons, and oxygen has 6 valence electrons. And so that gives me 12 valence electrons to play with. Who's in the middle? Well, it's not hydrogen. All right, and so it's probably going to be carbon. All right, carbon likes to be in the middle, all right, because we haven't learned about electronegativity, because oxygen is more electronegative than carbon. We'll get to that. And so I have carbon in the middle, O, H, H. Now, does it matter at all? Could you rotate this? Could you have written it HCOH or HHCO? All those work, okay? Do not worry about that. All those work. All right. So let's bond them. 2, 4, 6, 8, 10, 12. Fantastic. Duet, yes. Duet for hydrogen, yes. 2, 4, 6, 8 for oxygen, yes. 2, 4, 6 for carbon. That's a no. That's a no-go. All right, this is not good. How do we remedy it? Well, I have extra electrons on oxygen here, so I can raise 2, and we could form a double bond. Oh, didn't work. There we go. Double bond between oxygen and carbon. And now carbon has 8. All right, moving on. Carbon, again, has 4 valence electrons. Oxygen, 6. And chlorine has 7. So we have, what is that? 24 electrons. Wow. Who's in the middle? Well, even though, right, this is where it comes into play. Hydrogen is written first here, and carbon's in the middle, and we put carbon in the middle. Here, carbon's written first. I have oxygen and chlorine, right? There is no hydrogen, so carbon's written first. Carbon's going to be in the middle. All right? That may be confusing. That may not be confusing. As soon as we do electronegativity, you'll learn that oxygen and chlorine are more electronegative, and so they're not going to be in the middle. So let's say carbon's in the middle, and let's say we draw it very similar to the one we just did. All right, so we have more electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Is that good? Well, I would say no. Why not? Well, all your terminal atoms look great, but the central atom does not. And so we are going to take 2 away from oxygen and double bond again. Now, why did I pick oxygen? Why didn't I pick chlorine? It's a great question. I'm glad you asked it. All right. There's something coming up called formal charge. But let's talk about preferences. You guys like preferences? Oxygen, right, has its valence electrons 2, 2, and 1, 1, right? How many bonds do you think carbon likes to form, or oxygen likes to form? 2. Oxygen prefers 2. If you look at chlorine, chlorine has 7 valence electrons, and so chlorine likes to make 1 bond. That's their preference. Now, atoms don't always get their preference. They don't always get it, all right? But if they have a preference, oxygen will make 2 bonds, and chlorine will make 1 bond. And so if that's an option, right, because of the valence electron, the Lewis structures, right, that's what we'll do, okay? And so that's kind of how we know now. We'll actually get to more detailed and a better form of predicting later on. Sulfate. How many electrons? Well, we have Sulfur has 6 electrons, valence. Oxygen has 4 times 6 electrons. And then this -2 means we get to add 2 more electrons to it. Right? So that would be what, 32 electrons? Right? Oh, I missed it. Let's try this again. 4 and there's 6 there. There we go. That makes it a little bit better. Who's in the middle? Well, sulfur is written first, so we'll put sulfur in the middle. 4 oxygens. And our brackets. So this thing is 2 minus. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Is that okay? Well, I think so. Each oxygen has 8. Sulfur has 8. Right? Now, later on, we might change this a little bit. But right now, the octets are full, and we're happy. And it's a valid Lewis structure. So, right? That's the important part. It's a valid Lewis structure, so we're going to keep it. That's good. Acetate. Oh, I wanted to do... Let's not do acetate. Let's do... erase that. Let's put an H there. Let's do HC2H3O2. Let's do acetic acid. All right. How many electrons do we have for acetic acid? Well, 1 for hydrogen, plus 2 times 4 electrons for carbon, plus 3 times 1 electron for hydrogen, plus 2 times 6 electrons for oxygen. Wow. That's a lot of electrons there, isn't it? So we have, what is that, 8, 12, 24 electrons. Now, how is this arranged? Right, this becomes more complicated, right? We just dove into the deep end here. Well, how do we do this? Well, middle, I have 2 carbons. I'm going to put the 2 carbons in the middle. Right now, I have... If we talk about preferences again, carbon here. Carbon has 1, 2, 3, 4 preferences, right? Okay, so typically speaking, C's and H get along real well. Now, if you saw acetic acid, sometimes you'll see it written CH3COOH. Because it's written that way, because it's bonded that way. Let's try it. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, right? We filled in the duets of the hydrogens. We then fill in the octets of oxygen, and we're good. And is everything okay? This hydrogen check. This hydrogen check. This hydrogen check. This hydrogen checks out. Carbon, 2, 4, 6, 8, carbon check. Oxygen, 2, 4, 6, 8, check. Oxygen, 2, 4, 6, 8, check. Carbon here, 2, 4, 6, no, not enough. So what do we have to do? Make a double bond, don't we? We have to make a double bond. So we make a double bond. Now it works out. Okay. Now there is actually more than one way to do this. All right, with acetic acid. So I'm telling you that's the correct way. Go ahead on your own. Try to figure out a different way to bond these that works. All right. That's kind of fun. All right. Well, I hope that helped. That's the end of day 21, and we'll see you in the next one, guys. Take care.